Okay, let's get started. The remaining section of chapter 11. Okay, in the previous lecture, we have talked about the motion control with the velocity input. Now, this control input type will be changed into the torque from the velocity. So, the title of section 11.4, motion control with torque or force input. Actually, we are using the many kinds of core robot system. Core robot system is making use of the torque control input, not velocity control. Okay, in the previous long time ago, the most industrial robot systems utilize the velocity input to make the desired motion, but now the trend is changed. So we are focused on motion control with the torque or force input. Okay, the robot control engineer don't want to use velocity control input. A long time ago, we have used it for electric motor because this kind of velocity control algorithm do not make use of the dynamic model. So if you want to apply your dynamic model to your robot system, then we should use torque control input. Instead, robot control engineer use amplifier in the torque control mode, not velocity control mode. So input would be the desired torque or force. Actually, this torque and force is applied using the electric current because electric current is proportional to the electric torque using the proportional constant of torque constant. Okay, maybe you know that. Torque will be proportional to electric current. The proportional constant will be the torque constant. Actually, it is driven. It is driven by Fleming left-hand rule. So, if you wanted to get some more information, then you can Google or with the keyword motor operation principle. Okay. This allows the robot control engineer to use dynamic model of the robot in the design of a control law. Okay, I will skip the last sentence. Let me move to the next issue. Okay, motion control of a single joint. Okay, this is the pin joint. The electric actuator will be equipped here. This is the center mass of the link. So the gravity direction is like this. So we have the gravitational poles, and then the r is the distance from the rotation axis to the center of mass. Okay, let's denote the computation using the generalized coordinate theta. Okay, in here, let's write down the equation of motion. Newton's second law said to me the inertial force, the inertial torque will be equal to sum of external torque. Is it right? Okay, let me write down. The inertial torque will be the m theta 2 dot. M is the scalar inertia of the link about the axis of rotation. Such as the IZZ. Okay, in the previous lecture we have talked about it. M is the mass. Okay, and then R is the distance from the axis to the center of mass of the link. And then let's assume that the rotation movement will have the viscous friction. So viscous friction coefficient is the B. It acts in opposite direction of a movement. Okay, inertial torque will be the m theta 2 dot. Okay, we have the three kinds of torque or moment. Okay, the applied torque by the motor, and then mgr cosine theta. It will be the gravitational torque, and then minus b theta dot as a friction. Okay. So we have equation of motion like this. It will be used for design designing the controller here. Okay. By combining these two terms denoted by the H, actually this type is the generalized equation form for the robot system. Okay, I will use it to develop the control. Okay, feedback control, PID. Okay. Okay, here robot arm dynamics is here. Torque will be applied. Torque will be composed of three kinds of things: proportional error here, proportional gain, and then take your integration, and then integral gain here, and then derivative, and the derivative gain here. By combining three terms, we will call it PID control. Okay, so PID control is written in a mathematical format like this. This is error, integration error, derivative error. Okay, as you know, all the gains, control gains will be positive. Okay. Okay, maybe in the physical meaning, the KP act like a virtual spring, and then KD act like virtual damper, and integral gain can be used to reduce or eliminate steady-state errors. Okay. Okay, from the PID control, let's assume that integral gain is 0. It will make the PID control into the PD control. And then we will assume that the robot moves in the horizontal plane. That means gravitational torque will be the 0. Okay, so m theta 2 dot plus b theta dot will be equal to torque. Okay, the control input torque will be the PD control. So Kp theta E plus Kd theta E dot. So we have this equation. Okay, and then we will assume one more. Okay, this is first assumption, second assumption, third assumption is that it is target is given by the set point. It means desired theta will be the constant, any constant, but desired theta dot and the 2 dot will be the 0. Because we will assign just the constant value to the target. So theta E 2 dot, error 2 dot will be the minus theta 2 dot because the theta desired 2 dot is the 0. Okay, one more, the theta error dot will be the minus theta dot because theta dot is the 0. Okay, so by using this kind of terminology here, this is a minus theta E 2 dot, theta E dot, and we will get this equation. Okay. Okay, let's make the monic form. Monic polynomial form will be the highest coefficient will be the 0. Let's make it as a 0. I'm sorry, as a 1. So 1 over m will be applied to every element. So we have this equation. Okay, this is called as monic polynomial. Monic polynomial. Okay, let's compare the standard second order differential equation. Okay, the second term will be equal to 2 zeta omega n, and Kp over m will be equal to omega n squared. So by comparing both each other, then we can get the zeta and omega n. So by increasing the Kp, then the response will be the fast because the omega is increased. On the other hand, if you increase the Kd, derivative gain, then the damping ratio will be increased. So the stability is better than the previous one. Like this, we can assign the stability and the performance by adjusting the Kp and the Kd. Okay, let's assume that we will choose critical damping. That means it will be the 1. Okay, so we have a one constant equation. So Kd or Kp is determined. The remaining part will be the automatically determined, okay, because we will use the critical damping. Okay. Okay, let's extend the PID control or PD control into the PID. At that time, we can get the third order aerodynamics. it is a little bit different from the second order. Okay, let's extend. The set point is the same, but the horizontal plane will be changed into the vertical plane. So we have the gravitational torque. So mgr cosine theta will appear in the dynamics. Okay. With the same PD control, the aerodynamics will be like this. Okay, including the gravitational torque. Okay, let's assume that it is stay at the steady state. At that time, this will be the 0, and then the spring, the Kp theta E at the steady state, it will be 0. We have the this equation. Okay, the joint comes to last at the configuration, satisfying this equation. Okay. Okay, let's write down again. Kp theta desired as a constant and theta and mgr cosine theta. It must be the linear equation. So for given theta desired, theta will be determined using this equation. Okay, so final error is not 0. Okay, the theta will stay satisfying this equation. Okay, like this, in the presence of gravitational torque, we cannot eliminate the error at the steady state. But if you increase the Kp, then theta E, the error will be reduced, but it cannot be 0. Okay, so at the time, we can add the integral control to eliminate error. Okay, to eliminate steady state error, we return to PID control. So the previous PD control will be extended to the PID, including the I gain. So positive Ki gain will be assigned. Okay, so we have this equation one more. As mentioned before, this is the steady state is some constant because, as you know, this equation. Okay, so let's assume that at the steady state, let's take the one more time derivative. Then the second derivative will be the third derivative like this. Okay, so one more derivative is taken. So we can get this equation. In here, the gravitational torque is assumed to be constant because we assume that the robot system robot system stays at some configuration. So we will assume that this is the 0. Okay, because the theta stay at some point. Okay. Okay, let's if you take the characteristic equation, then we can get a third order polynomial in terms of the s, Laplace variable s, and by dividing on m for all terms, then we can get this equation as a monic polynomial. Okay, in order to determine the stability of a third order system, we will apply the Laus stability criterion. Laus stability criterion is composed of two conditions, necessary condition and the sufficient condition. Necessary condition is that the order coefficient should be positive. Okay, positive. But every gain is positive, so B is positive, then necessary condition is automatically satisfied. Okay. Okay, sufficient condition is to make the Laus table. Okay, third order 1 and Kp over m. The second order will be the B plus Kd over m, Ki over m. Okay, then the next step will be this one minus multiplying both sides and then divided by this one. So we can get this element. Okay. This element can be obtained Kp over m minus Ki over m over b plus Kd over m. So this is cancel out each other. Then we can get this equation. Okay, this is a 0, so this part is up here again. So first the column should be positive to guarantee the stability. Is right? But we know that every element is positive, so we just check this equation. Okay, Kp is larger than b plus Kd Kim. If we want to rewrite this equation in terms of Ki, then Ki is smaller than Kp b plus Kd over m. As mentioned before, Ki is positive, so we have this constraint. Okay, this is the result to guarantee the stability of the PID control. So Ki gain cannot go infinity because to guarantee the stability. Okay. On the other hand, the root-locus method will provide some information about the stability. Okay, we will use the critical damping at zeta as a 1. Okay, the characterization is like this. Okay, let's choose the gain as a bearing gain to describe the root-locus. Okay, the remaining terms will be the denominator of this part. So in order to draw the root-locus, we should write down the classification like this. Okay, so 1 over plus Ki like this, because the zeta is assigned as a 1. So from this equation, these terms should be equal to s plus omega n squared. By expanding this equation, then we can compare both sides, then we can determine the Kd and the Kp to obtain this equation. Anyway, this is the starting point of root-locus, Ki s plus omega n squared. This is 1. So according to the information of root-locus, if Ki is 0, then the closure pole will stay 0 and the minus omega n and the minus omega n. So at 0 Ki, the closure pole stay here. Okay, Ki is to 0. Ki is to 0. Okay. Then these three poles will meet here. Okay, one pole will go like this. Another pole will go to the right. This pole will go to the left. After meeting here, then this will be diverge. Okay, like this. The asymptotic angle will be the 60. Okay, maybe the asymptotic point from here. So maybe a asymptotic line here and here and here. So we can write down the root-locus. If you wanted to check this point, at that time, Law-Salvage criteria in the previous slide should be applied. So we can get this condition from here. Maybe both are same. This condition will be obtained at this point. Okay. Okay. If you are not good at the root-locus method, I'd like to recommend you to you can get many information from the undergraduate level control system technology, but this is not core in robotics. So if possible, you should study the root-locus method and the Law-Salvage criterion. But if you don't have much time, you can skip. Okay, the PID control has one issue, such as PID control can be saturated with the maximum control input level. At that time, the integrator anti-winder method can be applied. This is very well known and very effective. So you can use it. You have the saturation problem. Okay, this is a pseudocode of PID control. Okay, initially time is 0. The integral error will be assigned as a 0. The previous Q value is assigned as a measurement of the Q. And then this is the loop. This part will be repeated. Okay, the desired trajectory is generated, so QD and QD dot will be obtained from this function, and then Q is measured from the robot system, and then Q dot is calculated using the current Q and the previous Q by dividing the sampling time. And then the Q will be assigned the previous Q to calculate the Q dot the next time. And the error Q will be the QD minus Q. E dot will be the Q desired dot minus Q dot. The EINT, previous integral error, is used to write down to obtain the current integration error. The previous error plus E times sampling time. So we can add the area every instant, and then PID control is applied. The torque will be applied to the robot system. Okay, like this we can write down. We can make your own PID control. Okay, now we will extend the simple PID control or independent PID control or decentralized PID control to the dynamic control method. So to begin with, we will start feed-forward torque first. Okay, another strategy for trajectory following is to use model of robot dynamics. So as you know that this is the robot dynamics, let's apply the desired trajectory, desired acceleration, desired trajectory, and the desired velocity. Then we can get the desired torque. If you apply this kind of desired torque, then the robot system will follow this trajectory, but it has some error because the controller is implemented in this digitized form, but the actual robot system is analog. So there is some difference between both. There is some discrepancy. Okay, so the error will be accumulated according to the time progress. So we should add this controller, such as PID or PD. Okay, the feed-forward control should be added to the PID or feedback control. So this term, okay, we will add the PID to here. Okay, PID. All practical controller use feedback and feedback plus feed-forward because a good model can be used to improve performance and it can simplify the analysis. Okay, let's assign the desired aerodynamics. Okay, we can make the aerodynamics like this. As you know, the acceleration error will be obtained Q or theta desired 2 dot minus current acceleration. Okay, so we will attach our controller to the acceleration. So this is the main part. So let's move to the here. Then we can get this equation. Okay, let's assume that the inverse dynamics here. We will apply this control, acceleration control to here. Okay, then we have this one. Okay, this is called as inverse dynamics control, in short IDC, or it is called as a computed torque controller, CTC. So it has two names, IDC, inverse dynamics control, or CTC, computed torque control. Okay, this is a very famous one. In here, it is the independent joint control for the multi-joint system, but the M transform independent joint acceleration into the joint torque. Okay, so joint torque and the joint acceleration is different. Maybe the inertia matrix inertia matrix has the off diagonal term, so inertia matrix will rotate and maximize or minimize something like that using the principal axis or minor axis. Then we can get the joint torque. Okay, so the role of the M transforms the acceleration into the joint torque. Okay, this figure 11.18 shows the IDC or CTC. Here, desired acceleration and desired position and velocity. Using these two terms, we can obtain theta E, and then feedback control. Using the concept of PID control, we can determine the independent feedback control law theta 2 dot. It will be added to the theta desired 2 dot. This is the theta 2 dot. Okay, this theta 2 dot is applied to the inertia. Inertia matrix transforms the joint acceleration into the joint torque, so we can get joint torque. Okay, this torque is supported by the nonlinear terms. Okay, let me write down the torque again. Torque, inertia, and theta desired 2 dot plus PID control, and then H theta dot. Okay, the PID control will be equal to theta desired dot minus theta dot, and the KD gain, KP gain, theta desired minus theta, and integral gain, integral 0 to time t, theta d e tau, this is t, and theta t should be integrated using some integration variable t here. Okay, this is the PID control. Okay, maybe you can use this pseudocode to implement the CTC or IDC. Okay. Okay, let's move to our attention to the control or into the multi-joint. Actually, we have talked about multi-joint again already. Okay, it's not difficult. The independent joint control is extended to the n-joint robot system, but we are not good at the terminology, so we will introduce two kinds of terminology. Okay, two types of control for robot system. The first one will be the decentralized control. Another one will be the centralized control. Independent joint control will belong to this category. On the other hand, inverse dynamic control or CTC belongs to centralized control. Okay. In the case of decentralized control, each joint is controlled separately with no sharing of information between joints. Each joint information will contribute to each joint. There is no sharing information between both. On the other hand, in the case of centralized control, the full state information for each of n joint is available to calculate the control for each joint. Okay. Okay, as you can see here, there is no sharing information, so it is called as independent joint control. Is it right? Okay, the diagonal matrix can be used to determine the joint torque from the joint error. Okay, this kind of independent joint control will be used for gantry type XY table, such as XY table. On the other hand, highly geared robot system, in the absence of gravity, maybe at that time we can get the diagonalized inertia matrix big diagonal, the very small off-diagonal terms, it can be approximated to the independent joint control. Okay, at that time, the independent joint control will be effective. Okay, on the other hand, centralized control is useful in the case of gravity, and maybe the low energy, low gear ratio is used for your robot system. At the time, the inertial matrix cannot be diagonalized. Okay, at that time, we should apply the decentralized control law, such as the IDC or CTC. So this control law is used for the robot system. Okay, let's check the stability. Globally, asymptotic stability. Okay, the very famous one is the PD set point control. Okay, this stability was proven by the Arimoto sensei. He has proved this PD control stability in 1981. The first paper is about the without gravity, and the second one will dealt with the gravity again. Okay, the PD control set point PD set point control is applied. This is set point, is right? Because theta desired dot is 0, theta desired 2 dot is 0. So without gravity, so we have this dynamics. Okay, as you can see here, the capital C is about the Coriolis and the centripetal term. Okay, this is the closed loop system of the PD set point control without gravity. Okay, so let's assume that in total energy written by the kinetic energy and potential energy. Okay, this is the kinetic energy of robot system. This is the spring-like potential energy. Okay, so we will use this virtual energy. Okay, according to the time progress, this energy is decreased. At that time, the robot will lose the energy. So the robot system will be stable. That's the concept of this Lyapunov function. Okay, let's take the time derivative of the V to check the energy is reduced or not. Okay, so V dot here, by taking a time derivative, maybe this term appeared 2 times, so 1/2 disappear. And then the theta 2 dot appears twice, so 1/2 removed, and the m dot will appear. Okay, here m theta 2 dot is equal to this one from the closed loop dynamics in the previous page. Okay, closed loop system. Okay. Okay, here m dot and the minus 2c can be combined, and then this term and these terms appear again with the opposite sign. So we have one more terms here. In the previous in the chapter 8, m dot minus 2c is a skew symmetry. Okay, in the case of skew symmetry implies the zero diagonal term, and the off diagonal term has the negative sign. Okay, let's apply the x1 and x2, and the x1 and the x2. Okay, let's calculate it. Maybe this is the minus x2, this is the x1, and then x1, x2, then minus x1, x2, plus x1, x2, so we have 0. Okay, in the case of the skew symmetry matrix, if you multiply the front side and the back side, then we can get the 0 as a scalar. So remaining terms will be the minus theta dot transpose kd theta dot. Okay, we can say that without whenever non-zero theta dot, the energy will decrease because this is a negative. Time derivative of energy is negative, so it means energy lose. energy will reduce to the zero. But theta dot is zero. What happened at the time is non-zero. This is a zero. Okay? We should check this condition at the closed system. The closed system like this, we will check theta dot is 0. This is 0 and 0. Theta dot 0 implies theta 2 dot is 0. So we have this equation. Okay? So let's consider this Kp is positive. Theta desired 1 theta will be the 0. So this is, it must be the positive. So theta goes to theta desired. It means theta will go to target. Is it right? It is assured. Okay, this is called as Lasalle invariance principle. So according to the Lasalle invariance principle, the total energy, error energy decreases monotonically, and the robot converges to rest at theta d from the initial state. Okay, so PD control will guarantee the stability and the performance. Okay, stability, the total energy will decrease and the error will go to the zero. Okay. Okay, the section 4.3, task space motion control. Till now, we have talked about the joint space control, is right? Okay, so joint space control trajectories are naturally described in the joint variable, and there is no issue about the singularity and redundancy because we are performing the control in joint space. The joint space, desired joint trajectory and the velocities are obtained from the trajectory generation function. So there is no issue between the mapping from the task to the joint. Okay, so in the case of the joint space control, we don't have any issue about the singularity and the redundancy. But if the robot interacts with the external environment and objects such as the your hand palm on the desk, it may be more convenient to describe or express the motion as a trajectory of an end effector in the task space. Is right? Let's assume that your palm is located on the desk. If you wanted to push your hand palm forward, maybe the desired trajectory should be described in terms of task space, not joint space. Joint space is not simple. Okay, so let the end effector trajectory is specified by the XSB, space frame to the body frame, the end effector, and body twist. Body twist matrix form will be obtained X inverse times X dot. Okay, so using from the given end effector trajectories, we will choose one of the method. The first method will be this one. Okay, the first option is to convert trajectory, the end effector trajectory into joint space using the inverse kinematics. Okay, it's very natural way. Okay, we know that for the kinematics, in the level of position and in the level of velocity using the Jacobian, okay, the joint space trajectory is obtained from the IK. Okay, this is IK. We can determine the theta desired, and using the Jacobian Stowe inverse, we can determine the theta dot desired, and then from this equation, we can determine the desired acceleration. Okay, but in here, we have one drawback. We should know the Jacobian Stowe inverse and the Jacobian time derivative. Okay, it is singular. At that time, we cannot apply this method to the control. Okay, on the other hand, we can write down the total controller in terms of task space variable. Okay, so second option is to express robot dynamics in task space coordinate. Okay, actually we have obtained it in section 8.6. Okay, recall that the task space dynamics. Maybe you know that this is the length, this is the acceleration of a twist. Okay, nonlinear terms are here. This is the task space inertia. Okay, for given task space dynamics, let's assume that aerodynamics. Okay, it is the task space aerodynamics. Maybe you know that desired twist should be changed. The coordinate should be changed into the desired to the body. So this adjoint map should be applied. Is it right? At that time, this part will be the body twist in terms of body plane and effector plane. So it must be the velocity error. Okay, by taking a time derivative of this velocity error, then we can get the acceleration error. So the first part should be differentiated like this, and then v will be the minus v dot. So this equation is equal to the acceleration error. And then this is position error. Okay, position error is obtained by the log transform xsb inverse xsd. Then taking a logarithm, then we can determine the 4x4 matrix. Then from here we can extract a 6-dimensional xe. Okay, so this is the position error. And then taking a time derivative, we can implement the integral error. From here, this part can move to here. Okay, like this. It will be applied to the here. Then we can complete the inverse dimensional control in the task space plane. Okay, so this length, body length will be applied to the J transpose FV to obtain the joint torque. Okay, so this is the FV. In here, this acceleration will be exchanged from the aerodynamics. So the remaining part without the V, this one, will be applied to here. So we can get the desired acceleration, proportional control, integral control, and velocity control. So PID here. Okay, this is the desired acceleration. Okay, and then the nonlinear terms. The every terms are described in terms of the task space. Then J transpose will perform the coordinate mapping from the task space to the joint space. Okay, the first term, as mentioned before, this is the p-pod acceleration expressed in the actual and effector plane. Okay, and then the computation error xe belonging to R6 satisfied this logarithm matrix. Actually, the xe is the twist expressed in the end effector plane. If followed per unit time, okay, the per unit time the unit twist is obtained, that will be used to describe the error. So this will be used as a twist per unit time. Okay. Okay, velocity error. Maybe you know that this is the desired twist in terms of body frame. Okay, this is the actual body frame, body twist. So by subtracting both each other, then we can get the velocity error. And then the other joint, this part expressed the reference twist by VD. It is expressed in the XSD, so it should be exchanged into the body frame using this one. Okay. Okay, now we finished the first lecture of a 14 week. Okay, the remaining part will be the pulse control and the hybrid control and impedance control. Those are a kind of a pulse control method. Okay, till now we have talked about the motion control with pulse and the torque input. Okay, this part is the core of the chapter 11. So you should study again and again. And then if you have some question, you can email me including your questions or comment. Thank you.